In today's fast-paced world where we constantly juggle various responsibilities and pressures, it is important to address an issue that affects millions of people worldwide: depression. Depression is a mental health condition that can have a deep impact on a person's thoughts, emotions, and overall well-being. It often involves complex interactions within the brain, such as imbalances in neurotransmitters and proteins such as serotonin, klotho, and brain-derived neurotrophic factors, which play a role in regulating mood. The goal of our project is to develop a BrainBand that will effectively transmit electrical stimulation to the brain and help reduce the symptoms that are associated with depression. This includes creating a BrainBand that effectively transmits electrical stimulation to the brain, upregulating proteins related to reducing depression, makes even contact with the skin surface, and is a comfortable and portable device. We want to provide an alternative method of treating depression without requiring the intake of heavy medications that often result in worsening of symptoms. Two of the main components of our device are the sponges that go on top of the electrodes, as well as the saline solution that the sponges are dipped in for even electrical current delivery to the brain. For the sponge, we experimented with different sizes, thickness, and materials such as polyurethane and cellulose. For the saline solution, we created and tested 4 different saline concentrations and tested them for pH as well as resistance and conductivity on the sponge at 2 different locations. From these resistance values, we calculated and plotted conductivity and found that the 25 cm² cellulose sponge with an 80 millimolar saline solution is the most effective.
To deliver the electrical current to the brain, we used a pair of conductive rubber electrodes with snaps. There were several different electrodes out there ranging from metal to fabric types to square and round in shape and to pin and snaps for connection. Here we chose a conductive rubber material as it minimizes chemical reactions at the electrode skin interface, as it is non-metal, and with its round shape it minimizes edge concentration of the current. With the snap button design, it allows for the electrical current to distribute evenly over the skin and to better house the wires in the internal band housing. Regarding the size, the electrodes have a 25 cm² surface area, as it gives the optimal current density of 0.08 milliamps per cm² to stimulate the brain without causing excess skin irritation. Now going to how the current penetrates the brain.
2 models, human and rat models, were created using Soterix medical software to emulate the current flow and density within the brain during the 2 milliamp stimulation. The human model included an anode at F3 and a cathode at F4. In comparison, the rat model included an anode at B1 and a cathode at B2. Both locations of these electrodes are associated with the brain's prefrontal cortex, which are responsible for regulating thoughts, emotions, and actions. The results below are the coronal, sagittal, and axial slices of each of the brain's current and flow density through the brain. From these models, we can zoom into spherical models and see that the current travels through the deep brain tissue into the fornix and thalamus, which are responsible for producing serotonin and BDNF, 2 proteins associated with happiness.
As part of the prototyping process, a thermal finite element analysis was performed to ensure the electricity passing through the electrodes would not heat them to the point of burning the user. This assumed all of the energy passing through the electrodes would be converted into heat rather than being transmitted into the brain, and was multiplied by a factor of safety of 3 for a total of 27 milliwatts. The convection coefficients were assumed to be merely 1 watt per meter Kelvin for the external facing surfaces and 0.1 watts per meter Kelvin for surfaces inside the band. The components were modeled as their respective materials, with the exception of the sponge, which was modeled as water, assuming that it has been wetted and that the water's thermal properties would override the sponge's. The results demonstrated that even under these worst of circumstances, the electrodes would not exceed the average temperature of the user and remained well below the FDA regulatory temperature of 42 degrees Celsius. The max temperature the electrode reached was 36.7 degrees Celsius, and it could be observed in both the steady state and transient analyses that more heat transferred from the skin of the user to the electrode than vice versa. A drop test was also performed, but due to the lack of sufficient hardware, the simulations were too simple for any meaningful information to be drawn from them.
Going to our actual prototype, we have created a user manual about the device and how to use it, but I'll be demonstrating it here. It consists of a stimulation unit provided by the HDM company that we can customize what stimulation parameters we want. Here we would use a galvanic setting as it sends a direct current, and we can set that stimulation time to a typical session, which is 45 minutes. To connect the BrainBand to the stim unit, we connect the anode and cathode lead wires to each side of the band and plug that into either channel 1 or channel 2 in the polarized side. Before wearing the device, the user will add roughly 8 ml of the 80 millimolar saline solution to each sponge so that it is damp but not dripping, and place that on the electrodes to start the stimulation. Once it starts, we can then adjust the intensity to 2 milliamps and up to maximum of 3 milliamps. To see if the stimulation is working, we can use a multimeter to read if there's a current output. In this case, we do see a 2 milliamp reading, indicating that the BrainBand does work.
This project took the course over 2 quarters. In the first quarter, the team used the engineering design process, focusing on concept generation, prototype selection and development, and design simulations. We then fabricated the first prototype and used this as our basis for second quarter. Going through second quarter, we continued to revise the prototype through testing, tuning, and analysis of material selection and mechanical function for 6 weeks, and we are here today with the final prototype, which is generation 2 of the BrainBand.
Hello, I'm Athena. I'm the team lead, and I focused on the soterics modeling and wet lab studies.
Hello, I'm Sylvia Catania, and I'm in charge of testing the saline and the sponges.
Hi, I'm Sydney. I'm in charge of the design and manufacturing of the electrodes.
Hi, my name is Matthew Wise, and I was in charge of the design and mechanical engineering for the team.
And with that, we'd like to extend our sincere gratitude to our DepressiStim sponsors, which were the Leonhardts, as well as our UCI faculty advisor, Professor Farsad, and the team, which included Athena, Sylvia, Sydney, and Matthew. Thank you.